Okay, so before turning to computations of derivatives, I want to discuss a small other application concerning approximations. This will certainly come back, I think, in lecture 5. And we again recall, for the, I think, third time, the picture of our mountain, the height of which is described by the function f. So we're sitting at a point with coordinate a, we have the height f of a, we compare it to the point with coordinate a plus h, where you have height f a plus h. And what we discovered is that if we let h become smaller and smaller, then the slope of the linear function passing through these 2 points approximates the slope at the point where we're sitting. And the slope of the point where we're sitting is in fact the slope of the tangent line at the graph of the function f. Now, and the slope of this tangent line equals the derivative at a, so what we get is that the derivative, and it's precisely the way it was defined, is equal to the limiting slope. So it's equal to the limit for h to 0 of the difference in heights divided by the difference in points with the coordinates that we consider. Now, if h is very small, so suppose a plus h is somewhere here, then of course this quotient starts to be very closely, starts to resemble the slope at our tangent line. So in that case, the expression that we get, this quotient, is approximately equal to the derivative. Now this curved equality sign stands for approximately equal to. And obviously we have to take h small. Depends, of course, how small is still another topic which we will address, but this will come later. Now, suppose you're doing observations or numerical calculations. Well, with numerical calculations, you may not be able to plug in a precisely. So if a is the number pi, then instead of pi, you will have an approximation of pi. So you can view a plus h as an approximation of a, or if you make observations in the real world, then of course your observation may have some error. This h precisely is equal to the error that you make in your observation or in your data. It is an error in your input. Now, of course, making errors in your input has an effect on the output. Instead of f of a, we get f of a plus h. So this difference in the numerator over here will represent an error in the output. And what this quotient with this relation here tells us is the following, is that the derivative is approximately equal to an error in the output divided by an error in the input, but we can take the denominator over here to the left hand side, so what we get is that the derivative multiplied by an error in the input is approximately equal to the error in the output. And this tells you a lot of things. Just a small example and then I will summarize this. So if we have our function equal to x squared, we computed the derivative, and suppose that we have our point with coordinate 1/2, then we have the derivative at that point is equal to 2 times the point is equal to 2 times 1/2 equals 1. So what does it mean if we look at this relation is that the error in the output is approximately equal to the derivative at 1/2 is 1 multiplied by the error in the input, so it means that error in output and error in input are approximately equal. However, if we are sitting on a point with coordinate 100, then the derivative is equal to 2 times 100 is 200, and so the error in the output is now not approximately equal, but it's blown up by this, the value of the derivative. It's 200, so it's 200 times the error in the input. Or maybe it's better to write it here. So you see that the errors are blown up horribly. But it also tells you that if you are in a position in a point with coordinate which a very steep slope, then the accuracy of your observation needs to be much higher than in a point with a very flat slope. And so this is the thing that you should remind, that this derivative is in fact a measure for the required accuracy of your observations. If your accuracy is low, but you have an input variable with a very high derivative, then the result will be bad. And if your derivative is very small, then your output will be quite well.